Section 2.5.4. Avoid ambiguous hashing with Tuple Hash. In this chapter, I have talked about different types of cryptographic primitives and cryptographic algorithms. This included the SHA-2 hash function, which is vulnerable to length extension attacks but is still widely used when no secrets are hashed. The SHA-3 hash function, which is the recommended hash function nowadays. The Shake and C-Shake XOFs, which are more versatile tools than hash functions because they offer a variable output length. I will talk about one more handy function, Tuple Hash, which is based on C-Shake and specified in the same standard as C-Shake. Tuple Hash is an interesting function that allows one to hash a tuple, a list of something. To explain what Tuple Hash is and why it is useful, let me tell you a story. A few years ago, I was tasked to review a cryptocurrency as part of my work. It included basic features one would expect from a cryptocurrency: accounts, payments, and so on. Transactions between users would contain metadata about who is sending how much to whom. It would also include a small fee to compensate the network for processing the transaction. Alice, for example, can send transactions to the network, but to have them accepted, she needs to include proof that the transaction came from her. For this, she can hash the transaction and sign it. I gave a similar example in Chapter 1. Anyone can hash the transaction and verify the signature on the hash to see that this is the transaction Alice meant to send. Figure 2.17 illustrates that a man-in-the-middle attacker who intercepts the transaction before it reaches the network would not be able to tamper with the transaction. This is because the hash would change, and the signature would then not verify the new transaction digest. You will see in Chapter 7 that such an attacker is, of course, unable to forge Alice's signature on a new digest. And thanks to the second pre-image resistance of the hash function used, the attacker cannot find a totally different transaction that would hash to the same digest either. Is our MITM attacker harmless? We're not out of the woods yet. Unfortunately for the cryptocurrency I was auditing, the transaction was hashed by simply concatenating each field. What appeared as totally fine actually completely broke the cryptocurrency's payment system. Doing this trivially allows an attacker to break the second pre-image resistance of the hash function. Take a few moments to think about how you could find a different transaction that hashes to the same digest, 3, 4, D, 6, so on. What happens if we move one digit from the fee field to the amount field? One can see that the following transaction hashes to the same digest Alice signed. And thus, an MITM attacker who would want Bob to receive a bit more money would be able to modify the transaction without invalidating the signature. As you probably guessed, this is what Tuple Hash solves. It allows you to unambiguously hash a list of fields by using non-ambiguous encoding. What happens in reality is something close to the following, with the double pipe string concatenation operation. The input is this time constructed by prefixing each field of the transaction with its length. Take a minute to understand why this solves our issue. In general, one can use any hash function safely by always making sure to serialize the input before hashing it. Serializing the input means there always exists a way to deserialize it, meaning to recover the original input. If one can deserialize the data, then there isn't any ambiguity on field delimitation. Section 2.6. Hashing passwords. You have seen several useful functions in this chapter that are either hash functions or extend hash functions. But before you can jump to the next chapter, I need to mention password hashing. Imagine the following scenario. You have a website, which would make you a webmaster, and you want to have your users register and log into the site. So you create two web pages for these two respective features. Suddenly, you wonder, how are you going to store their passwords? Do you store those in clear text in a database? There seems to be nothing wrong with this at first, you think. It's not perfect, though. People tend to reuse the same password everywhere, and if, or when, You get breached and attackers manage to dump all your users' passwords, it will be bad for your users, and it will be bad for the reputation of your platform. You think a little bit more and you realize that an attacker who would be able to steal this database would then be able to log in as any user. Storing the passwords in clear text is now less than ideal, and you would like to have a better way to deal with this. One solution could be to hash your passwords and only store the digests. When someone logs into your website, the flow would be similar to the following. 1. You receive the user's password. 2. You hash the password they give you and get rid of the password. 3. You compare the digest with what you had stored previously. If it matches, the user is logged in. The flow allows you to handle users' passwords for a limited time. Still, an attacker that gets into your servers can stealthily remain to log passwords from this flow until you detect its presence. We acknowledge that this is still not a perfect situation, but we still improve the site's security. In security, we also call this defense in depth, which is the act of layering imperfect defenses in hope that an attacker will not defeat all of those layers. This is what real-world cryptography is also about. But other problems exist with this solution. If an attacker retrieves hashed passwords, a brute force attack or an exhaustive search, trying all possible passwords, can be undertaken. This would test each attempt against the whole database. Ideally, we would want an attacker to only be able to attack one hash password at a time. Hash functions are supposed to be as fast. Attackers can leverage this to brute force many passwords per second. Ideally, we would have a mechanism to slow down such attacks. The first issue has been commonly solved by using salts, which are random values that are public and different for each user. We use a salt along with the user's password when hashing it, which in some sense is like using a per-user customization string with C-Shake. It effectively creates a different hash function for every user. Because each user uses a different hash function, an attacker cannot pre-compute large tables of passwords, called rainbow tables, hoping to test those against the whole database of stolen password hashes. The second issue is solved with password hashes, which are designed to be slow. The current state-of-the-art choice for this is Argon 2, the winner of the password hashing competition found at password-hashing.net that ran from 2013 to 2015. At the time of this writing, Argon 2 is on track to be standardized as an RFC. See this link. In practice, other non-standard algorithms like PBKDF2, bcrypt, and scrypt are also used. The problem is that these can be used with insecure parameters and are thus not straightforward to configure in practice. In addition, only Argon 2 and scrypt defend against heavy optimizations from attackers as other schemes are not memory hard. The term memory hard means that the algorithm can only be optimized through the optimization of memory access. In other words, optimizing the rest doesn't gain you much. As optimizing memory access is limited even with dedicated hardware, there's only so much cache you can put around a CPU, memory hard functions are slow to run on any type of device. This is a desired property when you want to prevent attackers from getting a non-negligible speed advantage in evaluating a function. Figure 2.18 reviews the different types of hash functions you saw in this chapter. Summary. A hash function provides collision resistance, pre-image resistance, and second pre-image resistance. Pre-image resistance means that one shouldn't be able to find the input that produced a digest. Second pre-image resistance means that from an input and its digest, one shouldn't be able to find a different input that hashes to the same digest. Collision resistance means that one shouldn't be able to find two random inputs that hash to the same output. The most widely adopted hash function is SHA-2, while the recommended hash function is SHA-3 due to SHA-2's lack of resistance to length extension attacks. Shake is an extendable output function, or XOF, that acts like a hash function but provides an arbitrary length digest. C-Shake, for customizable shake, allows one to easily create instances of shake that behave like different XOFs. This is called domain separation. Objects should be serialized before being hashed in order to avoid breaking the second pre-image resistance of the hash function. Algorithms like TupleHash automatically take care of this. Hashing passwords make use of slower hash functions designed specifically for that purpose. Argon 2 is the state-of-the-art choice.